Welcome to International Conference of Research Advancement, IRA Network 2019, and together with Journal of Advanced Research in Fluid Mechanics and Thermal Sciences Academia Baru. My name is Muhammad Adrian Thomas. Today, I will present my findings on reconstruction of 3D models using close-range photogrammetry method for CFD applications. The content for today's presentation are, I'll begin with the abstract, into the research background, to the proposed method for analysis, to the post-processing, and finally the conclusion. Without further ado, let's begin with the abstract. The main objective of this paper is to present the use of close-range photogrammetry method to create a 3D model of a small-scale car for CFD modeling. This 3D model is created in Autodesk Recap software, where it is then imported into SolidWorks to perform the airflow simulation. Therefore, in this study, the minimum and maximum vortices created by the 3D model car are about 0.04 per second and 1555.59 per second respectively, with a velocity airflow of between 0 to 50 meter per second. Into the research background, in the automotive engineering field, to develop the correct model for in-depth studies through CAE simulation are not an easy task and very time-consuming. These studies are usually conducted using conventional methods such as Moore projection, triangulation method, 3D laser scanners, and more. However, these traditional methods are very expensive to execute and difficult for data analysis. What are photogrammetry methods then? Photogrammetry is an engineering code of practice that has spread by the revolution of computer science. Therefore, the drastic increment in the computer utilization has heavily influenced on the photogrammetry application. The word photogrammetry is derived from three Greek words, which is phot, gamma, and metrin, that denotes as light, drawing, and measurement respectively. The photogrammetry method can be divided into two main groups, which is the far range, that branches into aerial and terrestrial techniques, and the close-range photogrammetry method itself. The close range is to obtain information of the object closer for further studies. In such cases, such as thermal studies or the CFD investigation. The similarity between the photogrammetry and the conventional methods are they are applicable to all 2D and 3D surfaces. They are very effective to large volumes of data collection, and they are capable to analyze good and bad features of products. However, the difference between both methods are photogrammetry methods are much more cheaper compared to the conventional methods, and the digitizing stages are not tedious, and photogrammetry do not require any extra supports compared to the conventional methods. Also, photogrammetry methods require shorter time for processing and produce the 3D model efficient compared to the conventional methods. Thus, the advantages of using the photogrammetry methods are it can be utilized in certain areas that are hazardous, troublesome to reach or investigate, it is inexpensive, very fast and efficient, and photogrammetries are applicable to most industrial platforms. Into the proposed method, in this research, the preliminary test is conducted by taking a total set of 144 images around a sample small-scale car model using an iPhone 7 Plus smartphone camera. These images are shot at every 5-degree angle in a full loops from two different heights, top and bottom rows, as shown in the figure. The images have to be shot in good exposure time with a soft lighted surrounding. This is to avoid poor acquisition as well as the reconstruction from being blobby. Those selected images are then uploaded into the Autodesk Recap software to develop the 3D model. Enhancement on the 3D model is also made to smoothen the constructed geometry using Mesh Mixer. Optimizing the model is an optional step if those meshes in the region of interest of the model required repairing or filling the holes. The 3D model is then imported and launched to the SolidWorks software. In this research, the CFD analysis of external flow geometry over the model is investigated and closed cavity are considered. This is to exclude any internal space and cavity without flow conditions. The final step is to create a computational domain shape for the flows all around the model, as shown in the figure. Also, it is advisable to keep the computational model small as possible that fits the whole 3D model entirely. This is to provide the result which is more efficient and precise. Into the post-processing, this figure depicts the pressure flow visualization. The simulation displays that the pressure remains low when it passes from the front to the top and back of the model, as presented by the blue contour. Moreover, at the inclined front and rear windscreen of the 3D model car, there are increase in pressure around these regions that are presented by the red-yellow contour. This is due to the sudden angle differences between the hood and A-pillar, boot and seat pillar, respectively. In this figure, the model is set at the standard atmospheric pressure, which is 101,325 Pascal, and therefore the car model body is subjected on equal pressure. However, this is not the case for the tail lights, as the pressure ranges of 101,800 to 102,400 Pascal, displayed by the green contour. The pressure flow in this region increases because it approaches narrower gap between the tail lights and the back fenders. In this picture, it shows the velocity flow visualization. The highest velocity flow magnitude is created at the hood of the car as it turns into a free stream far from the model. As the flow rises along the front side members of the model, the velocity flow increases, approximately 33 meter per second, that is shown by the red-yellow contour. This could be the result of the developed stagnation point in that region. In this figure, the flow trajectory are simulated using the average magnitude. The figure portrays the airflow at the A-pillar of the photogrammetric car model that are presented at both the top and bottom region respectively. This flow separation phenomenon has occurred due to the aerodynamic shape of the car model. So this is the velocity in the x-axis, which lies between 0 to 50 meter per second. And this is the air velocity in the z-axis, which lies the same speed between 0 to 50 meter per second. This is a picture for the vorticity. Thus, a maximum vorticity is observed at the back of the car. This is due to the formation of free shear layer that lifts the edges of the car model and roll ups, causing a chaotic motion of lower vortices. The maximum vortices is about 1,558.59 per second, and the minimum is 0.04 per second. The photogrammetric method is used to produce a mesh model in the study for the subsequent computational fluid dynamics study. The complex feature and shapes can be very challenging and hard to create using CAD drawing, for instance SolidWorks in certain case study. Therefore, the technique does not only extract the surface information precisely, but also generate an accurate 3D model instantly. The photogrammetric method is used in study because it is more convenient to move the camera around the object compared than using 3D scanning equipment instead. As mentioned previously, the photogrammetric data acquisition works with the image recognition to develop the photogrammetric 3D model. This reconstructed 3D model can be then imported to be used as the computational model for the following CFD analysis. As a conclusion, the use of photogrammetry technique in the beginning of the study is to develop a precise 3D model for the CFD studies. The analysis of the airflow studies over the computational model have consistently shown an excellent results. As a consequence, the post-processing results shown by the analysis are very reliable and concise. Also, the simulation illustrated by the computational car model in the study are satisfactory, and the fundamentals of CFD studies are largely intact. In future, creating high quality photogrammetric model can enhance the accuracy of the fluid flow investigation. Thank you very much.